right, welcome back. We're going to continue our look at sort of how to best present data. The only difference is now we're switching from categorical data to quantitative data. All right, so there's going to be different tools that we have at our disposal when we're dealing with this type of data. So remember, quantitative variables are those whose values are numbers and an average makes sense. So what do I mean by make sense? Zip codes are numbers, but there's no such thing as an average zip code. So that would be a categorical variable, even though the values themselves are numerical. So again, it's got to make sense to calculate an average. So the most basic tool we have for describing or displaying quantitative data is the dot plot. So a dot plot is where each value or each data value is represented by a single dot above its location on the number line. All right, so you go through your data, you look at the value, you make a dot wherever that value is, and then the dots just stack up on one another. All right, and this just sort of gives you a visual summary of what's going on with the data. All right, so you can more easily see kind of what's happening without having to try to pick apart each individual data point. All right, it's also good because it gives us a visual, and then it sets us up to start describing the distribution of a quantitative variable. So that's a question that I'm going to ask you over and over and over again in this class, is to describe the distribution. All right. Now, when I ask you to describe a distribution, there are 4 different things that you need to be thinking about. You need to be thinking about the shape of the distribution. So you should always comment on the shape of the distribution. You should talk about the center of the distribution. You should talk about the spread of the distribution. And you need to talk about any potential outliers that could affect the distribution. So what we're going to now do is we're going to go through each of these in more detail. Like, what do I actually mean when I ask you to describe the shape? What do I actually mean when I ask you to describe the center? What do I mean when I ask you to describe the spread? And then how are we establishing outliers? But these are the 4 pieces that I need you to be commenting on. So anytime I say describe a distribution, I'm expecting you to comment on these 4 pieces. And if you don't comment on those 4 pieces, you're probably going to lose points for ignoring them. All right. So first things first, shape. All right. And this is where that dot plot comes in handy, because it gives you an idea of the shape of the distribution. They're either going to be skewed left, symmetric, or skewed right. Now, there's different amounts of skew, but for the most part, we'll just be like, oh, it's really skewed or it's slightly skewed. We won't get that exact, but more just kind of use general terms to sort of describe it. Now, a skew means that you have one tail that sort of goes off in one direction or the other. So you've got sort of the bulk of your observations, and then they sort of trail off and reach more extreme values in either in an upper direction or in a lower direction. So one way to help remember this is skewed. Sounds a lot like ski. All right, and you would ski to the right here. All right, that's the way the mountain kind of goes. So do you love my beautiful skier there? So skewed to the right, you can also think as ski to the right. Isn't that clever? Aren't I clever? You're so impressed right now. I know you're on video and you can't really express your gratitude for this memory device, but you're welcome. I know. And this one is ski to the left. All right, so we've got symmetric, which is kind of balanced. You know, you've got most of your observations in the middle, and then they go off to either side in sort of a balanced way. Here, you've got most of your observations to the left, and then the tail goes out to the right. Here, you have most of your observations to the right, but then the tail goes out to the left. So it's the direction of the tail that dictates whether it's left skewed or right skewed. A lot of times people are like, oh, there's more observations, so this must be left skewed. Nope, it all deals with the tail and which direction it sort of extends out in. All right, so this one extends out to the right, so it's skewed right. This one extends out to the left, so it's skewed left. All right, so if I ask for the shape, you're making one of these three comments. The other thing that you can comment about the shape regards the mode. All right, so the mode, as you normally think about it, is, oh, whatever observation appears the most. Okay. Yes, that's still true, but when we're talking about the shape, mode is actually going to be referring to local peaks in a distribution. So a distribution can have one modes, two modes, at which point it's called bimodal, or more, which is multimodal. So right here, this would be considered a bimodal distribution. All right, so this would be a bimodal distribution, which again is a description of its shape, because you have one mode here and you have another mode there. Those are our local peaks. Now, when you're determining whether something is a local peak, don't overanalyze it. And here's what I'm saying. So let's say you have a histogram that looks something like this, and you've got a bar that goes up, and then you've got another bar that goes up, and then you've got another bar that might be like slightly lower, and then you've got another bar that's slightly higher, and then maybe you start coming back down at that point. All right. So sometimes kids are like, well, technically this is a peak, then you go down, and this is another peak. Don't overanalyze it. You know, when you're gathering data, sometimes you're going to have little blips like this. This is your peak. All right. This would be a unimodal distribution. This right here does not count as a peak. All right. They should be distinct peaks like you have here and here. All right. Little blips like this do not count as like a separate peak when you're describing a distribution as either unimodal or bimodal. So again, if there's obviously two peaks, then yeah, point that out when you're describing the distribution. It's bimodal, but don't overanalyze it. Don't be like, yeah, well, technically this goes down and then it goes back up. So no, all right, this is a unimodal distribution. This right here is a bimodal distribution. All right, so those are the pieces that you need to be aware of when describing the shape. You need to be able to differentiate between symmetric, left skewed, and right skewed. You need to be able to differentiate between unimodal, bimodal, multimodal. All right. Next, the center. All right. So the value that divides the data roughly in half. There are two primary measures we use when we're talking about center. One is the median, which is the halfway value when the numbers are ordered. So basically the middle value when you have everything in order, but obviously they have to be in order, otherwise it's not really the middle. And then just a quick note here, if there are an even number of values, average together the two middle values. And this is stuff that you've done before, so I don't really think I'm telling you anything new, but you know, who knows the last time you've actually had to do this, so just using it as a refresher. So obviously if you had something like 3, 6, and 7, 6 would be your median, but if you had something like 4, 5, 6, 10, all right, your median would be the average of these two, or 5.5. All right. So again, just depending on whether or not you have odd or even number of values. And then mean, I'm not going to complicate this. I'm not going to give you a big, long, sophisticated definition. I'm just going to say the average of the values. So you add them all up, you divide by however many values there are. Okay. So we have these two measurements. When do we use which? All right, so why have two different measurements? Should we always give both? Do we only give one? And if we only give one, which one do we give? All right, so let's talk about the advantages and the disadvantages of either measurement. And that's going to then inform which one you want to be using when you describe a distribution. So the mean. Let's do 0.1 here. All right. The good thing is that it takes all values into account. All right. To calculate the mean, you have to use every single value in your data set. So you're not leaving anything out. You're not like summarizing. I mean, you're summarizing, but you're using every single piece of information that you have. The downside is that it can be drastically impacted by outliers. All right. So let's compare that to the median. So the downside of the median is that it really only uses one or maybe two values. So everything else is kind of ignored. You're just looking at whatever number ends up in the middle. All the other quirks or intricacies of your data are lost because you're just looking at one or possibly maybe two numbers. All right, so that's a downside, but their upside is that makes it more resistant to outliers. So, given those advantages and disadvantages, generally the rule of thumb is that we use the mean when the data is symmetric, and we use the median when the data is skewed. All right. And the idea there is that when you have a skewed distribution, so let's say I have this distribution where it goes off to the right, these values might be considered outliers, right? Because they're being dragged way out there. And those outliers can pull the average way up and give a misleading representation of the center of your distribution, whereas the median is going to ignore all of that. Like this one value isn't really going to affect the median because the median really only uses one or two different data points. All right, and this is just sort of a silly example here, but the mean salary for a geography major graduating from the University of North Carolina in 1986 was $22 million. All right, that's not because graduating from UNC with a geography degree is that lucrative. It's because that was the year that Michael Jordan graduated from UNC with a degree in geography. So his one value is bringing everything way up and providing a misleading picture of the center of the distribution. Right? When you have something that's symmetric, presumably any high values are being balanced out by low values, so you're ending up in the right area, whereas that might not be true with a skewed distribution because you might have some really high values, but not any really low values, and then this drags it up and gives you a misleading picture. So that's something that you have to be aware of, that based on the shape of your distribution, you should be providing me with a different measure of center, whether it be the mean or the median, depends on the shape. All right, next, the spread. How much variability is there in the data? So how spread out is the data? Is it all concentrated in a small area, or do you have some really high values, some really low values? Is it really sort of spread out? All right, so the simplest way that we can establish how spread out things are would be to calculate a range, right? And again, this is where you have to avoid using like the English version of the word range and focus on the statistics version of the word range. So when I ask for the range, I'm not looking for, oh, it's from 2 to 10. I'm looking for the difference between the highest so I'm going to put max and lowest. So I'm going to put min value. And then just to make sure we're super clear on that, it is only a single value. So whenever you're calculating the range, it should be one single value that you're reporting. All right? It shouldn't be, oh, it's from 2 to 10. If the min was 2 and the max was 10, you should be saying the range is 8. I'm getting a range of 8. All right, now there are other measures of spread that we're going to look at. All right, one is standard deviation, and the other is the interquartile range. We're not going to focus on those today. Standard deviation is a pretty big concept in stats. It's pretty foundational. So we're actually going to spend some more time looking at that one specifically. But just for right now, we'll just use range to talk about the spread. But as we get further in, we're going to switch over to standard deviation and interquartile range because they give you some more insight into what's happening than just the range. All right. And then last but not least, outliers would be an individual or value that falls outside of the overall pattern. So if we've got sort of our graph right here, way out here would represent an outlier. And eventually we are going to actually specify with a calculation what counts as an outlier. But that calculation requires the interquartile range, which we're not talking about right now. So we're going to hold off on that. So for right now, again, you can just say any individual or value that falls outside of the overall pattern counts as an outlier. So we'll keep it simple for the time being. All right, moving on. Now that we know the 4 ways that we're going to be describing it, all right, shape, which then we're talking about skew or unimodal, bimodal, multimodal, center, mean or median, spread, right now range, but eventually interquartile range and standard deviation, and then outliers are sort of points that break from the overall pattern. All right, so Next, let's talk about another visual way that we can represent data, right? And something went wrong with this printout. I apologize for that because the key is right on top of the data. Not super useful. I will fix that, but for the time being, it doesn't really matter. We'll still be able to kind of do what we're doing here, even though that printed out like that. Whoops. All right, so another tool that we have that's a little more sophisticated than just our simple dot plot is the stem plot. All right, also sometimes called the stem and leaf plot is a display that shows the shape of a distribution while maintaining the individual values. All right, and why do I say while maintaining the individual values? Well, if you think about like a histogram, which we'll get to later, all right, you lose some of the individual values because they're sort of condensed down into these bars. A stem and leaf plot is going to keep the individual values so that even when we're looking at the shape of the distribution, we still know the exact values that were part of the original data set. So the example here is we have how many pairs of shoes do runners have? All right, and we've got data, 50, 26, 26, 31, 57, 19, 24, 22, and then a bunch of mystery data that I've blocked out for some foolish reason, 30, 32, 13, 50, and 51. All right, so the way a stem plot works is we sort of break the number down into two pieces. We break it down into a stem and then the leaves. The value of your stem is going to depend on like the size of the numbers that you're dealing with. So for these numbers that range from like 13 to 57, the stem is representing the tens place and the leaves are representing the ones place. All right, so the way this breaks down is this right here is a stem of 1 and a leaf of 3. So we've got 13, 13, 13, 15, 19, 22, 23, 23, 24, 26, 26, 30, so on and so forth. Even though we have no 40s, we still include the 4 here because that visually shows us that there's a gap between those two things. So values should always be in order. All right. There should be no commas. They need to be evenly spaced out because if you don't evenly space them out, you're losing this idea of shape. You know, if I crammed one all together, then it would make it look shorter than it actually is. And then include all numbers on the stem. That's what I was just talking about. You don't want to eliminate a gap. Like the gap is there. It's part of the picture. Make sure that you can still see the gap so you don't skip that there. All right, so those are kind of the main things that you need to keep in mind. Now, occasionally you're going to make one of these and you're going to end up with a picture that doesn't really give you a whole lot because so many of the observations end up in a single stem that you might have to split the stems. So split the stems when there are a few stems. It gives a better picture of the distribution. So let me add to this. Each stem should cover an equal number of values. So, for example, we've got this 0 here. All right, there's a large number of zeros here. Maybe when we want to break this down into two separate stems, we'd want to make sure that each one had an equal number of values. So one of the zero stems could go from 0 to 4. Another zero stem could go from 5 to 9. But each of those is representing 5 different values: 0, 1, 2, 3, and 4, and then 5, 6, 7, 8, and 9. You wouldn't break them down in a way that the two stems could, like one could have 3 and one could have 7, or one could have 4 and one could have 6. They should always have an equal number of values that they represent. And we can see an example of this. This is that same graph, only represented with split stems instead of single stems. So the 0 gets split into two pieces. 0 through 4 gets in the first piece. 5 through 9 gets in the second piece. And then if we're splitting them, we split all of them. All right, so we wouldn't just split 0 or just split 1 because they had a lot of observations in them. If we're splitting, everything gets split. And again, that's important to keep the spacing. So just a note here is all stems are split. All right, and this is where that box that is in the wrong spot is supposed to be, because you always should have a key with these so that somebody can know exactly how to read your stem plot, because we're going to see that you can have stems that are not just the tens place. So then it's important that the reader of your graph knows what you're actually referring to. So again, this is just another way, and usually we do this if you end up with like a couple of stems that are just really long compared to everything else. This breaks it apart a little more and gives us sort of a better picture of what's actually happening, the shape of the distribution. Now, this is great if you just want to analyze a single distribution. When we want to compare two different distributions, for example, how many shoes runners own versus how many shoes bowlers own, because that's what we all do in our free time, then we switch over to the back-to-back stem plot. So when you make a back-to-back stem plot, the stem goes in the middle. And the two groups are compared on opposite sides. All right, so make sure that you label each side so that you know which one we're dealing with. This is the runner side, this is the bowler side. And then you basically just make two stem and leaf plots. The bowler side would go out to the right, the runner side would go out to the left. And then it gives you sort of this visual comparison. Now, again, if we split one, now we're splitting both. So originally we didn't split the runner chart, we only split the bowler chart. But now because we're splitting them for one, we obviously have to split them for both. So it gives you sort of an apples to apples comparison. And we can see that, there's like a few bowlers that have a lot of shoes, but for the most part, the bowlers are at the lower end of the scale, and you've got the runners a little more spread out all around. So there'd be more spread in the runners. There's less spread for the bowlers. The bowlers have a lower center to their distribution than the runners do. The runners seem to be a little more symmetric. The bowlers seem to be a little more skewed because you have these out here that are stretching out to the right. For the bowlers, you'd probably label these as outliers. And then we're sort of getting into outlier territory here with the runners, but not quite as much. There are 4 different people that have up to 50 shoes here, so not quite as extreme. But, it sort of gives us a basis for comparison for these two different situations. Now, sometimes when you have a stem plot and you're dealing with larger numbers, it's not feasible to put the full value on the chart. All right, so there are times when we're doing these and we're going to have to truncate our results. So it says, don't be afraid to round or truncate. Now, what's the difference between rounding and truncating? When you truncate, you simply drop how do I want to say this? Drop the lower place values without rounding. All right. Or you can just think of this as automatically round down. So if you were going to truncate 5,672, all right, when we're doing a stem and leaf plot, we're not going to do a 5,000 stem and then 672 as our leaf. You know, our leaf is only ever a single value. So instead, we can truncate it and turn that to 5,6, and then 5,6 would just represent 5,600. So you'd never have something like this where it's like 672. Generally, you've got your stem, you've got your leaf. The leaf is only ever going to be a single digit. Now, there are times when your stem will have multiple digits. So let's pretend that my data ranged from, like I had data that was like 91, 92, 87, and then 104. All right, let's pretend my data looked like that. All right, your stems could go 8, 9, 10, and then your leaves would be the 7, the 1, the 2, and the 4 like this. But our leaves are only ever a single digit. So sometimes, depending on what we're trying to represent, we may have to round or truncate. And you should just specify what you're doing. Like, you know, if in your key you could say all values were rounded, or you could say all values were truncated. But you should specify so that the user reading the graph knows what choice you made. Did you truncate where everything was rounded down and you just basically cut off the lower values? Or did you round it so that, you know, this would have become 5,700 as opposed to 5,600? So you should sort of specify that when you're doing these. All right, but that's it. All right, this is kind of the first step into summarizing quantitative data. So again, we're moving away from categorical, and we're seeing that we have some different things and different tools that we're going to use. All right, you know, we've got the dot plot at the simple end of it. We're just making a dot above each value. Then we've got this idea of describing our distribution. So shape, center, spread, outliers. Again, with center, mean versus median, you want to make sure you know which one you're choosing. Mean when the distribution's symmetric, median when it's skewed. And then last but not least, we've got these stem plots that we can use to help describe what's going on and illustrate, sort of, again, give a visual illustration of what's going on. All right, so hope this was helpful. Have a good day, and I will see you later.